Okay, thank you so much. So this is Jun Sakuma, Weekend AIP. So today we are going to present several talks about AI security and privacy. So first of all, I'd like to show some announcements. Important notice about this seminar. Reproduction is prohibited. Reproducing all or any part of the contents is prohibited without the author's permission. The seminar will be recorded and the video will be available on the Weekend AIP website later. If you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. You can put questions or comments in the box. And if you have any question, please submit your question from the Q&A tab. Okay, then let's start. So today we have 5 talks and I am the first speaker. So first I'd like to talk about the realization of trustworthy AI. My name is Jun Sakuma from Weekend AIP and also from University of Tsukuba, and also the PI of the AI security and privacy team. So our team, this is a list of the team member. So we have one postdoc researcher, Jiayan Liu. He's working on the study of adversarial example. And also we have a junior research associate from University of Tokyo, Yue-san. He's working on the security of federated learning. And we have 6 visiting researchers and 4 of the visiting researcher is going to give a talk today. Professor Mori, he's an expert in the security in the real world. He's going to give a talk today. And also Professor Uno, he's an expert of the formal method. And he's going to give a talk about the connection between the formal method and machine learning today. Professor Yohei Akimoto is an expert of the black box optimization. So he's going to give a talk about the minimax optimization and its application to real-world problem. And Professor Kazuto Fukuchi is an expert of machine learning, especially in the fairness-aware machine learning. So he's going to present a talk about the fairness awareness of the machine learning today. And also many of works have been supported by students of machine learning data mining laboratory and black box optimization laboratory of University of Tsukuba. So I'd like to thank to all students. Okay, let's start. So as you might know well, nowadays, the predictive performance of AI is progressively and drastically improved recently. And as a well-known fact, the performance of objective recognition in images by AI is still improving. So when the performance of AI in more complex decision-making tasks outperforms that of humans, we can imagine that AI will make decisions in more critical situations that can affect our life and death, such as clinical medication, car driving, conflict resolution, employment, and so on and so forth. So when decision-making by AI is employed for such critical situations, what should be considered? So traditionally, the performance of AI is measured by to what extent the prediction is correct. And this measurement works well when AI is used for traditional tasks, such as numeric classification. However, when AI is used for high-stakes decisions, such as medical diagnostic imaging, we want that the decisions made by AI is not only correct, but also well-reasoned and ethical. This is because no matter how the prediction accuracy is good, we usually do not want to accept medical treatment that suddenly emerges from a black box that is decisions not supported by evidence sufficiently or without explanation. Also, if there is a suspicion that the treatment is designed for another purpose, such as for someone's benefit or for some kind of experiment, we usually do not want to accept such a treatment. So in order to realize artificial intelligence that can deal with high-stake decisions, our mission, the mission of our team is to establish secure and trustworthy AI. And this slide summarizes several requirements for realizing trustworthy AI. The first two are necessary conditions on decisions by artificial intelligence. The first one is expert level quality. It requires that, of course, the AI should have a good predictive performance or a good ability for decision making. And also, the AI is required to comply with the law. So these two are necessary conditions for trustworthy AI. And the third and fourth are constraints required for AI to be trustworthy. Even under expected changes of environments or attack by intentional malicious uses, the decisions by AI should be robust. So the resiliency to attack guarantees this kind of robustness. Also, for AI to be trustworthy, use of AI should not violate the user's privacy, and decisions by AI should not cause discrimination. In this sense, we should constrain that decisions by AI should respect human rights in any sense. And the last two are needed to verify the decisions of AI in a post hoc manner, which is particularly needed when decisions of AI is wrong or not so much reliable. The explainability requires AI to provide not only decisions, but also the reason why such a decision is made. And the traceability requires AI to clarify the process that the decision is made. And these issues need to be considered for AI to be trustworthy. So today's seminar have two talks about resiliency to attack. So this is a very famous example of attack against deep learning, and you might be fed up with these panda pictures anyway. So by adding a carefully designed noise into an image, we can see that the classification result of AI can be arbitrarily controlled without changing the acceptance of the image at all. So this is called adversarial example. And attaining the resiliency against such adversarial attack is important to establish trustworthy AI. And various kinds of defense methods, as listed here, have been presented last 5 years. However, for each defense method, an attack method that invalidates the defense has been proposed immediately. So the security of deep learning is called a never-ending arms race. Some people say working in this direction is meaningless because of arms race. But I would like to emphasize that this arms race itself contributes to establish trustworthy AI. So for reference, we show a brief history of defense and attack of cryptography. So I won't go into the details of the history of cryptography, but we can see that the arms race starts from the age of Roman Empire, and it still lasts as of 2021. And I would like to stress that the arms race that lasts for more than 2,000 years is inevitable to establish the modern information security. So in this sense, I believe that the arms race itself forms the nature of the security. which will be also true for the security of AI. So in this direction, we have two talks today. Professor Mori is an expert of security in the real world, and also he will talk about what a security researcher thought about the threat model and feasibility of adversarial examples. So he's going to present some concern about the intermediate field of machine learning and security. Also, Professor Akimoto will present about minimax optimization with approximate minimization solvers and its application to automatic birthing control. So the minimax optimization itself is an important tool to investigate the security and robustness of artificial intelligence. So maybe the technique introduced by this talk would be beneficial to the realization of the security of AI. Also, we have one talk about fairness awareness of artificial intelligence. When AI makes decisions, that has a large impact on our life. If the decision is highly correlated with some attributes, that should not be correlated with decisions such as gender or race. It causes discrimination. So Dr. Fukuchi will present a novel method to achieve fairness for regression tasks. Also, for verification of decisions by AI, Dr. Uno will talk about applications of machine learning in formal methods. So today we're gonna have 4 more talks about AI, security and privacy. So please enjoy. Okay, so this is the end of my talk. So if you have any question, please submit your question to the Q&A box. Okay, if you have no question, can we switch the speaker?
So I'm Kazuto Fukuchi, the visiting researcher at the AI security and privacy team of the Riken AIP. And I'm also from the University of Tsukuba. So today I'm going to talk about my recent work titled Equalize the Impact of Fair Regulation. And this is a joint work with Jun Sakuma, team leader. So this is a study about the fairness problem in machine learning. So I'd like to first introduce what is fairness problem. So many researchers reported the fairness issue in the real application, such as, for example, the Bromini all reported investigated several face recognition APIs provided to some company. And they found that the recognition accuracy of the darker female is significantly lower than other groups. This gap makes the unfair decisions. Another example is the hiring tool developed in Amazon. The Amazon developed the AI security tool that scored the applicant's resume for applicant resume. And they investigate the tool and found that the tool penalized the resume score if the resume contains the word woman. So the tool have a gender bias. So there is a lot of report about unfairness in machine learning, but I'd like to talk detail about the crime of unfairness problem in the crime risk assignments reported by Angry et al. In Profica. So they investigate the COMPASS algorithms, which is machine learning based algorithm for the receiving risk score prediction. So this algorithm predict the score risk of the prisoner that will be reopened in the future. So higher score indicate higher risk. So if we input this person to the system, then we get the score like 3. And their analysis showed that there is a prisoner that's labeled as a lower risk, but he is arrested 3 times after his release. But also there is a prisoner labeled by higher risk, but he's actually not arrested after release. So in the report, they also take statistics about this fact. In this table shows the ratio of the prisoner who labeled a higher risk but didn't reoffend, and the ratio of prisoner who labeled a lower risk yet didn't reoffend. You can see that there is a significant gap between this ratio of white and the ratio of African American. This result indicates that algorithm is actually incorrectly estimate African American as high risk, and also the algorithm incorrectly estimate the white as a low risk. So we can say that algorithm gives preferential treatment to white. So this is a real fairness issue in the real machine learning system. So due to this real problem, social community highly demand the fairness for such as machine learning-based systems. So one example of the demand is that White House reports provided in 2014. In this report, say that the increasing use of algorithms to make eligibility decisions must be carefully monitored for potential discriminatory outcome for disadvantaged groups, even absent discriminatory intent. And a similar statement appeared in the White House report in 2016. And also recently, the IEEE published a guideline for ethical issue in AI. In this guideline, fairness is recognized as an important issue for the trustworthiness of AI. Okay, this is so far I'm described what is a fairness problem in machine learning. Next, because of this, due to this, motivated by this concern, many researchers developed a lot of technique for mitigating bias of the unfair bias. So I like to first introduce a simple existing way to address this issue. So let's start from compass example. So this is the same table. So in this example, the difference between this and this ratio is problematic. And this ratio, that is algorithm incorrectly estimate African Americans higher risk, is recognized as a false negative rate of this classification model. And also, this ratio, the ratio of the prisoner level lower risk yet did reoffend is equivalent to the false positive rate. So one can think one may think of the fairness can be defined by equality of the false negative rate and false positive rate. So the hard et al. The equalizers developer hard et al. Its fairness definition employs such consideration. So that is fairness is equality of false positive rate and the false negative rate among the group made by the sensitive attribute. So because the false positive rate can be interpreted as a positive impact to the prisoner, because false positive rate is incorrect estimation, incorrectly estimates false positive rate is incorrect as a lower risk. So the prisoner receives the positive impact. On the other hand, false negative rate can be interpreted as the negative impact made by the classification. And equalizers can be interpreted as different bias injected by the learning process. So let's see this figure. This is a level distribution of a group A and a group B. And after learning process, the estimated level distribution is shown in right-hand side. So equalize odds requires the equality between these green area among the different groups. So we can interpret it that this green area is difference between the true distribution of level and the estimated distribution of level. So this is can be interpreted as a bias injected by learning process. So this is one of the fairness definition in the existing works, and the learning algorithm to mitigate this bias is to So to achieve this condition, there is a lot of technique to emphasize this condition in the classification algorithms. So in the classification case, the story is ended. The equalizers can be used for measure the unfairness in the classification, but I'd like to talk about today is the regression problem. So in which case the estimation is different from classification. In the classification, the estimate is a discrete value, but in the regression, the estimation is a continuous value. In the regression problem, we want to predict the outcome y, which can be, for example, let us consider the scenario where the company predicts the user's income for determining the credit line of the user. But the company didn't have information about the income, so using machine learning technique to predict the income. So the goal of regression task is to predict the income from such as credit history. So to this end, standard machine learning technique minimizes the regression error defined by the mean disformulation. And if we consider the fairness problem in regulation problem, we want to enforce some fairness definition for this regulation function. The one possible choice of the fairness definition is equalize odds described so far. But in reality, we need more deep consideration for the regulation problem if the equalized odds can be used for classification problem, but it can be failed to capture the fairness in the regulation problem. So to describe why the equalized odds fail in regulation problem, I like to introduce the notion of significance of adverse impact. So in the classification case, the impact, what we can consider is existence of the impact. So the prisoner just we know whether the prisoner receives a positive or negative impact. But in the regulation case, because the prediction of the regulation is a continuous value, the impact can be take the continuous value representing the significance of impact. So let's describe this using this example. So in this table, the left row shows the true income of two persons. Both of them are the true income of Alice and Bob are both $50,000. But the estimated income for the Alice and Bob are different. For the Alice, the estimated income is $48,000, but the estimated income for the Bob is $14,000. So if the credit line is equivalent to the estimated income, so how much credit line is lower is $2,000 for Alice and $10,000 for Bob. So because the Bob, how much Bob can lend the money is can be smaller than Alice. So we can consider Bob receives a more significant impact compared to the Alice. So in the regulation period, we need to take account of this difference of the significance of impact. So to take account of this significance of impact, I like show failure of the existing fairness definition equalized odds. So roughly speaking, equalized odds demand the regressor to make same prediction for individual with the same true outcome, regardless of the sensitive attribute. So for example, in this table, the true income is shown here and estimated income is shown here. So with the same true income, this regressor makes the same prediction in this table. So the regressor shown in this table is fair in the sense of equalized odds. The problem is the distribution of true income can differ by group, by which the significance impact differed by group. So for example, in this table, we depict the histogram of how much credit line is lowered by this figure. as you can see, the group B drop of credit line for group E is much higher than those in group A. So we can say that the group E receives a more adverse impact compared to the group A, even if this regressor satisfies equalizer impact. So we can say the equalizer impact cannot capture the difference in significance impact. So the goal of my study is to develop the mechanism for regression task that equalize impact significance. To this end, we propose a novel fairness definition equalize impact for regression problem. And also we developed the unfairness score that is a quantization of our fairness definition. And then we developed the efficient estimation method for our unfairness score. And our unfairness, we can calculate the gradient of our unfairness score, by which we can apply the standard first order optimization method for learning for the learning algorithms. And also we investigate the estimation error by theoretical analysis. So let's begin with defining the impact. So what is impact? Well, in this study, impact is a continuous value determined from the true outcome y and the predicted outcome y hat. So formally, the impact is defined by output of impact function. This is a function that calculated the impact value from the y and y hat. So the larger impact value denotes the more adverse impact. So the most simple case, the most simple credit line case as shown so far, the impact function can be defined the true income minus the predicted income. So in this case, the impact is just how much the credit line is lowered or rise. So another impact function can be a nonlinear function if needed. If the calculating the value of impact is more complex than this simple case. And impact forms a distribution because the significance impact is differed by individual. So we can draw this type of picture. This picture shows the distribution of the impact value for the two different groups. And the above figure shows the density function for the two different groups. The blue figure shows the density function for group A, and the red figure shows the density function for group B. And the corresponding cumulative distribution function is shown in the bottom figure. So blue line is a CDA for the group A, and the red line is a CDA for the group B. So from this figure, let us consider when the regressor is fair, when it is unfair. So by using an example, so let us consider the example where only the mean are different as shown in this figure. So that is mean of blue and red is different. So you can see that the density of red is in the light of blue figure. So we can say that the red is more red member in the red group is more adverse, receives a more adversary impact than member in the group blue groups. So in this situation, we should recognize the regressor as unfair. So this unfairness can be recognized by using the CDF figure. Like in this figure, red line is always in the light of blue line, meaning that the red group is always receives a more adverse impact than the blue group. Let us think of different situation where only the variances are different. So in this case, so we cannot say either of, you can see that we cannot say either of red or blue is more adverse, because we cannot say either of red and blue are positioned higher in this field. So this is a case where the two people is mixing this. So in this case, in the left half people, the red group receives a more advantageous impact than the blue groups. But in the right-hand side of here in this figure, the member in the red group receives a more adverse impact than blue groups, because the red figure is more positioned in the light of the blue figure. So this is more clearly seen from the 3DF figure. Like in the right side of this figure, the red line is always in the light of blue line, meaning that in the right half, the red group receives more adverse impact than the blue groups. Opposite is occurring in the left half. So because we cannot say either red or blue is more adverse, in this case, we should say the regressor is fair. So by using this, considering this discussion, we define the fairness for the impact. So maybe we can define the fairness by the equity between the total significance of adverse and advantageous impact. This can be depicted by the green and yellow area in this figure. So in the right half area, the red receives more adverse impact. So, and the difference between the blue line and the red line is the difference of the significance of impact. So this area represents the total significance of adverse impact. Similarly, the yellow area represents the total significance of advantageous impact. So we can define the fairness by equity between the gray and yellow area. So by this, we can recognize this case as fair. So the main technical issue is how we measure the green and yellow area. To this end, we introduce optimal transport cost defined by this function. crucial point is we use a carefully designed cost function. So in this cost function, we can see this cost function is a difference of blue and red line, a cost of blue and red line. And by using this cost function, the cost only incur if the red line is in the right or the blue line. So by using this cost function, we can measure only the green area by using optimal transport cost. So just if we denote the red distribution, this option Fs, and the blue distribution, option Fs prime, then the optimal transport cost using this cost function can be the green area. The yellow area is easily obtained by exchanging the input of these two distribution. So then equals our fairness definition is easily defined. We say F is fair if these two area, green and yellow area, is equal. So we quantify such a fairness definition equals impact. A way of the quantify the equals impact is easy. Just first we quantify the equality between the green and yellow area by just taking a difference of these two values. And taking maximum with a distinct group, we can define the unfairness score. So I also developed the estimation of the unfairness score. This is a estimation score. But in reality, this contains the sort operator. It makes this unfairness score is indifferentiable with respect to the model parameter. So, but we can show that the fairness score is actually locally discontinuous. So we can get the Clark's generalized gradient. By using this, we can apply the first order optimization. This is a standard way in the deep learning, such as if we employ the rail activation, the gradient is actually the Clark's generalized gradient. So our method is just minimizing this objective function. This contains empirical MSE and unfairness score defined so far. And this is a control parameter of the priority between the accuracy and fairness. So, and also we theoretically analyze the estimation error of unfairness score. So with some assumption, we show that the mean squared error of the unfairness score can be bounded by 1 over k, where the k is the sample size. So surprisingly, this bound is independent of the model complexity. So this is quite useful for deep learning because in the deep learning, the model is so complex. So I like to give some experimental comparison results with our method, with the existing method based on the equalized odds. Yeah, this is a result of the accuracy and fairness of the existing and our method. So this figure shows the horizontal line shows the unfairness score. So, and the vertical line shows the accuracy of the regressor, so MSE. So this in the left bottom position in the figure is the better one. So the blue point is baseline, and the orange and green line is our existing method, and red line is our proposed methods. And you can see that the proposed method, red one, success to run fair and accurate regressor by the choice of parameter. So this is quite surprising because our method simultaneously achieve high accuracy and high fairness. This is because of our fairness definition. Our fairness definition do not conflict with achieving high accuracy. So maybe I skip this slide. So let's conclude. We developed a mechanism for regression that equalize impact significance. So this can't be accomplished by the existing equalize odds definition. And yeah, this is the end of my talk. Thank you for listening.
So I'm Tatsuyamori from Waseda University. So I am a security researcher. So I'd like to share my thoughts on the adverse example from the viewpoint of a security researcher today. So I'm going to share some research questions that are not solved yet. So the goal of this talk is to share my thoughts on the adverse examples. And in this line, I will talk about threat model, feasibility, and the future research directions. And I also would like to share and discuss several recent studies along this line, including ours. And some of the research may not be necessarily machine learning algorithm research itself. And these are not the goals of this talk. I will not present the cutting-edge adverse examples generation or detection algorithms, and I will not discuss the theories behind the adverse example studies. So if you're interested in these topics, I'm sorry, but maybe you may find some interesting topics from my talk. Okay, so let me start with some basic security concepts so that we can share the base of this talk. So I think some of you may have already known this. So if you take the information security class, CI try is always written in the textbook. So it composes of 3 different concepts: confidentiality, integrity, and availability. So let's take out these terms one by one. The confidentiality is about to ensure the information is accessible only to those who are authorized to access it. And there are several technologies that can establish confidentiality: cryptography, access control, and authentication. So in terms of the machine learning, so there is a research directions which try to establish a confidentiality for machine learning, which we call privacy preserving machine learning, like a free homomorphic encryption and secure multi-party computation. And also recently, federated learning is one of the hot research topics in this area. The second one is integrity. We want to ensure that information is not destroyed, altered, now erased by someone. And we want to assure that information is consistent and trustworthy. So there are several technologies developed, like a cryptographic hash function, checksum, message authentication code, and digital signatures. So basically, these are based on the cryptography. And I also note that integrity can be applied to other disciplines, including software and machine learning. And I will talk a little bit about the integrity for machine learning later. The third one is availability. We want to ensure that the person or organization who are authorized to access the information can always access to that information 24/7. And it can be achieved by if we maintain all resources correctly, including hardware, network, and software, we can establish availability. And there are several technologies like redundancy, disaster recovery, backup, and denial of service mitigation techniques. And we can talk about machine learning here. So there is a service called machine learning as a service, and which is running on the cloud. And we want to protect machine learning as a service from the denial of service attack. So when we talk about the security for the machine learning, it is useful to think of this CIA triad. So I will introduce another interesting security concept, which is a little bit minor compared to the CIA triad. That is Courtney's law. So it composes of 3 different laws. And the first law states that you cannot say anything interesting or significant about the security unless you specify some context of the particular application or environment. So as a researcher, we want to generalize the things, but when we talk about the security, it is better to make some specific applications or environment to make the things interesting or significant. And the second law states that we can't spend more money than we can tolerate, which means we can't spend all the money into the security. If, of course, we need to have some other business, and which means we need to see some acceptable risk and risk analysis. So the risk assessment is essential. And here, let me write a thing. So generally, when we talk about risk, it's a product of the probability and the expectation of damage. So it is important to quantify these values to get something that is very important, which has a higher risks. And in other words, if the attacker have high incentive to make such attack, then we expect that the probability may large, which means that the risk is high. Okay, so it is important to think about the motivation behind the attack to correctly assess the risk behind the attack. So I will skip this third law because it is not related to this talk. So the next background is advanced example. And Sakuma Sensei have already shown the basic concept, but let me again use this image. I know that many of you have already seen these images a million times, but please bear with me. It is quite useful to share the idea. So we have an image, and that can be fed into the machine learning algorithm, and we generate some noise according to some algorithm. And this is a generated advanced example. It still looks like a panda. From the viewpoint of machine learning algorithm, the original image was detected as panda with fairly high confidence. But I think that 67 is not that high, but still, it looks like panda from the machine learning. And unfortunately, the advanced example changed the detection results. It's now detected as gibbon with quite high confidence. And this is an image of gibbon. What we learned from this example is that this word, gibbon, I have not known this word before. But anyway, so this is how advanced example works. So this summarizes the key idea of generating advanced example. So this is a first methodology that generates advanced example. And it was proposed by the Sujiti back in 2014. So we have loss function, which has already trained over the model of the data. And in terms of the weight and the input X and target class Y. And let me change the pointer here. Okay, so as we can access to the model, we can derive the gradient and in terms of the input space X. And to generate advanced example, we simply make use of this gradient because it can tell us the direction which will maximize the loss function, which will alter the machine learning classification results. And we also want to ensure that the perturbation is small. So we reflect the perturbation following the maximum constraints using the sign function. So it is quite naive because the gradient is now become plus epsilon or minus epsilon, but still it works quite well to change the detection results of the machine learning classification. Okay. And now I'll talk a little bit about the integrity. So originally, the data integrity means that ensures the consistency of data. And for the software, we want to ensure that consistency of the software behavior. even though we change the input, we expect that the output is same if the input is quite close. Okay. And for the machine learning, it is similar to the software. So even though we change the input a little bit, x plus delta, which is not noticeable to the human, we expect that output should be the same. So the attacker's goal is to violate this machine learning integrity. Okay. So in other words, the idea is to exploit the gap between human perception and algorithm. Okay. So now I'm going to share the interesting statistics, which is maintained by Dr. Nicholas Carney, who is working at Google Research. And he's quite active in this area and has published many research papers. Okay, so this is a cumulative number of adverse example papers and which were posted on the archive. So let me change the screen. Now you may see, oh, this is the wrong one, but let me change the tab. Okay, so here, this is a website maintained by Dr. Carney, and he is now automatically collecting the papers on the adverse example on the archive. So you can see quite a large number of papers appeared on the archive on the adverse example. So this ratio shows confidence that the Carney machine learning classifier tells whether it is actually about machine adverse example. But anyway, there are a lot of papers. So now switching back to the slide. So the question is, what will happen in the future? So we still have a lot of papers on this, and what we will see. So I made a simple analysis, the regression analysis, and this is a logarithm. This is a straight line, which implies that it is actually exponentially growing. Oh, by the way, this is a number of posted papers per year, not cumulative numbers. Okay. So what we can see here is that in the next year, we will reach to the 10,000, which is already quite huge. And 3 years later, it now reaches to the entire archive summation, which is quite huge. Wow. So all the papers on the archive may about the adverse example. 4 years later, it leads to the 10 million. Wow. So at this moment, we can say that we can rule the galaxy. I'm just joking. But what we can see from this figure is that it is just a naive extrapolation, but still we can say that so many researchers have been inspired by the first work. Okay, so why we are so interested in the adverse example? Let's see some example here. So it is possible to look into what kind of research discipline the researchers are publishing these papers, but I haven't done that yet. So instead, I picked up some recently posted adverse example papers from the archive, and that these colored strings show the discipline. And what we can see here that some papers are from the computer vision research community, and some are from the security community, cryptography and security, and some papers are from the machine learning community. So which implies the researchers outside machine learning community are actually interested in this topic. And as a security researcher, I can say that actually security researchers are very interested in this topic. And the third one is actually appear to the IEEE S&P this year, which is one of the top security conferences in the security research community. I will talk a little bit about this paper later if I have time. Okay, so now I'd like to share this research question. How feasible are these attacks that make use of adverse examples? Okay, so there are a couple of the weaknesses of adverse example. The weakness means from the viewpoint of attacker, there are some pivots that the attacker needs to overcome. And one is a physical constraint. And it is known that AEs do not work well in the physical world due to the noise or some other factors that are not considered in the simulation. Okay. And from the viewpoint of feasibility, there are two different aspects. One is a threat model. And yeah, adverse example actually works. But from the security problem, viewpoint, there could be alternative and which could be cheap and easy to deploy approaches that do the same goal. So why we need to use adverse example. Another concern is the system. So yeah, we can follow the machine learning algorithm, but if you take a look at the system, that should be come with many other modules other than the machine learning algorithm. So we need to take care of the other modules, how it behaves, to think of what will happen in the entire system. Okay, so let's take a look at these things one by one. So first, I will talk about the challenge in the physical world. So again, this is the work done by Carlini and Dr. David Wagner, and they generated audio adversarial example. The idea is this is a voice speech, and they fed it into the speech recognition machine learning algorithm, and they get text, which is good. And they created the adversarial example, and this is a audio adversarial example, which still look like hear like the same voice. But once it is fed into the machine learning algorithm, it gives a different text. So it could be the security problem because this text could be something like, okay, Google or Hey Siri or something like that, that will launch the, sorry, my kid just came into, so anyway, that will launch the voice assistant system. Okay, so that could be the problem. And yeah, they successfully generated such adverse example, but it was evaluated in the simulation. And we made a replication study, which is again simulation, not physical experiments. And the original speech was recognized as this one. Without the dataset, the article is useless by the deep speech, which is an open source voice recognition system. And they generated adverse example. Now it becomes okay, Google, OpenAV.com, which could cause a problem. And however, if they are fed into other voice recognition system, even though it is digitally transferred to the Google speech to text, we don't do any physical experiments. They did the attack was not successful, which means transferability was not successful in this case. So even in the simulation, it is not that easy to mount this attack. So to overcome this constraint, Yakura-san and Sakuma-sensei have published a paper on the robust audio adverse example or the physical attack, which is excellent work. And what they incorporated as a physical constraint is the existence of bandpass filter and impulse response, which could be representing the reverberation. And also they consider the Gaussian noise. And by combining these constraints into the loss function, they successfully generated the audio adversarial example that can work over there, which is nice. And so this is a joint work with Sakuma Sensei, which is still under submission. So it's about the adversary bits, which is the ECG, electrocardiogram diagnosis. So recent Apple Watch come with this functionality, so it can monitor your ECG. And the idea is, so this is ECG for the healthy person, and the adversary, this is adversary noise, and this is a generated adversary example for ECG. So it will lead to the wrong decision, arrhythmia, which may lead to another action, like the unnecessary treatment, medical treatment, and something like that. Okay, so again, we wanted to establish this attack in the physical environment. So there are several constraints we needed to take care. And we incorporated these constraints into the model and made some physical experiments. So in the simulation, I will skip the details, but the attack was successful in general. So we made some hardware experiment, and here's a patient. The person actually first of all did this, and we attach a sensor on the chest of the patient. Okay, so we have a controller which reads the sensor data, and We also made some adversarial device, so which reads the ECG from the sensor and make some timing and inject the perturbation into the signal. For this, we use the audio mixer. And finally, it will fit into the ECG diagram system, which is now working on the PC. But I will note that this is just a proof of concept implementation. Entire system could be embedded into a wearable device. Okay. So compared to the simulation case, the result was not that high successful rate, but I still say that we don't need to success all the heartbeats. But instead, if we see some arrhythmia, that may lead to the next action, like a medical treatment. So it still works in the physical environment. So this was another example of the mounting the adverse example in the physical world. So this is a work done by the researcher from the University of Washington. So I think some of you may have heard of this research. So it's about the road signs, and that could be led by the self-driving car. Okay. So what they did was to generate adversary patch, which is not trying to make the perturbation, but they physically made the patch that can be put into the object like this one. So their goal is to change the detection results. Now stop sign may look like the speed limit, 45 miles per hour. Okay, so they show that the patch is quite robust against the change of distance or angles, and also they change the color, they still work. That's good. And since it is related to the self-driving car, many people are interested in this study. But again, I would like to make some questions on this attack, on this the self-driving car attack. So do we really need to exploit the human perception gap here? Okay, the patch means that it still looks like a stop sign. But if the goal is to fool the self-driving car, if we are driving the class 1, 2, 3 self-driving car, the driver needs to take care of the driving. It is not fully automated. So we need to fool the driver as well. That's the first problem. And also, if we really achieve this attack, we have another possibly easy two-way approach to establish the goal. So just replace or install the fake road sign. Okay, it will cost something, but still it may work. So another concern is the motivation behind the attack, following the code in the second law. So who wants to mount this attack? To whom? For what reasons? It is not clear. And we want to specify this point as a security problem. And also, a self-driving car may have many other sensors or modules to establish the rigid safety. So we need to think of the other modules as well. Okay, so let's start with the reasonable threat model using adverse example, the second concern. Okay, so I am going to share some research results that look like reasonable threat model for me. Okay, so this is an evasive adverse example. In this threat model, the defender is ad blocking tool. Okay, actually the advertisement is quite annoying, so some of you may have already installed such ad blocking tool onto your browser like a plugin. And here the attacker is advertiser. The advertiser may want to deliver as many as advertisement to the users so that they can make the large revenue. Okay, so the attacker's goal is to evade the perception ad blocking. So perception means, so instead of using some signature or URL, now ad blocking tool is making use of the images to detect the new type of the advertisement. Okay, so it is kind of arms and legs. And so attacker goal is to evade the perception ad blocking. Why they aim to deliver advertisement to customers? So they still look advertisement to the customers. Okay, and so here is some examples. So these are not necessarily machine learning. So these are the techniques used to detect these images, which is one of the elements that indicate the existence of advertisement. And by adding some noise, they show that they can evade the detection mechanisms. And for this one, it is trying to evade the detection by YOLO, which is the object recognition algorithm, open source system. And yeah, it went successful. So for this one, I think the underlying motivation behind the attacker is quite reasonable. So this is another example, adverse explicit content. So due to the time constraint, I will skip this one, sorry. But again, these are the, this was one of the reasonable adverse example problem. So finally, I would like to share the challenge for the end-to-end systems, where we have some subsystems other than the machine learning algorithms. Okay, so let's take a look at this example, which express the machine translation. So we have input text and some pre-processing for natural language processing, and also machine learning, which could be neural network. And finally, we got the translated text. Okay, I know that some neural network could be also used for the pre-processing, but as far as we tested, it seems like the many machine translation service may take the form that look like this. So we don't have the ground truth, but this is just our conjecture. Okay. So for the advanced example, we will focus on the machine learning. But for the entire end-to-end system, we may also need to take care of the pre-processing. So we focus on this pre-processing. Okay. So here's an example. So sorry for those who are not familiar with Japanese. So this is English and this is Japanese. So it is a translation result. The act is illegal. It's now translated into this, which actually means this act is legal, the opposite. And it is impossible to fly, but it is now saying it is possible to fly. So you may have noticed that a little bit weird character here, L and M. Okay, so we make use some character that look like each other, what is called homoglyph. So these are completely different having character codes, but still they look like quite similar from the viewpoint of human perception. So we tested several translator in the wild, and they are actually vulnerable to this kind of attack. Okay, I will skip the detail, but this is one of the things we can think of. So other than attacking machine learning, we can attack this pre-processing part. So finally, let me talk about the self-driving car. So this is a very brief description of the self-driving car architecture. So the self-driving car comes with some sensors like the GPS and also LiDAR, which can detect the objects around the vehicle. And also we have the multi-sensor fusion, which combines the output of the multiple sensors that will come with camera. And based on the input from multiple sensors or cameras, the controller makes a decision based on the map, which is having the plan to reach to the destination. Okay. And finally, that controller makes the control over the steering and axle and brake, which is a lateral or longitudinal control. Okay. So for the entire end-to-end system, we need to take care of these things. Okay. And I also note that the controller makes use of several different algorithms, not only machine learning, but like the feedback-based control, like a Kalman filter. Okay. Also, the machine learning was vulnerable to the adverse example. If the control is using more robust feedback control mechanism, we need to take care of what will happen if adverse example is fed into the system. Okay. So rather than trying to look at the individual modules, we may now need to think of the entire system. That's a question I wanted to share with you. So due to the time limit, I will skip this. but this is one of the interesting research study. So let me summarize the things. So from the viewpoint of security researcher, adverse example is about machine learning integrity problem. And security problem, we need to ask the questions like, is this actually reasonable? And also, we want to ensure that attack succeeds in the physical world. And we also want to check whether it actually works for the end-to-end system. So these are the research directions, the formulating, evaluating adverse examples, and the various physical constraints. And also adverse input for the entire system. And now we need to take care of the system integrity. Okay. Sorry for the long time talk, and this is the end of my talk. Thank you.
Okay, thank you so much, Mori Sensei. So we have questions. So let me repeat the question. I read the question. One example is ECG adversarial attack. Since ECG is recorded by devices directly, I'm wondering how such ECG perturbations may happen in the physical world. Could you give some answer to this question, Mori?
Okay. So the question is about how we can inject this ECG adverse example. So one thing one possible way we inject this adverse example is to implement this kind of device into the wearable ECG device like an Apple Watch. It will be difficult to actually inject something onto the product like Apple Watch. But we are assuming that this kind of ECG system is cheap and publicly available for anyone. So someone will be able to add this kind of module onto the ECG wearable device. That's what we were thinking.
Okay, thank you so much. So for the second question, in the explanation of the adversarial example, the perturbation is denoted by delta. And as long as the input dimension is super high, because of the curse of dimensionality, definition of the neighborhood might not be straightforward. How do you think about this? This might be a difficult question to answer.
That may be true. So since I'm not a machine learning researcher, I may not be able to fully answer your question. But as far as I know, so there are several algorithms which I may not be able to explain well here. But in reality, it is not that we don't necessarily have to obtain the exact answer. But still, in many cases, the generated adverse example actually works in practice. That's what I experienced. And maybe Sakuma Sensei may be able to say some comments on this question.
I don't think I have a right answer, but maybe the sense behind this idea is that for example, in case of images, as long as appearance to human is not far different from the original image, that would work as an adversarial example. So maybe the distance itself is not seriously important, I think, in the sense of adversarial example. This is my impression. Okay, then let me introduce the third question. Is it possible to generate adversarial noise without accessing to the target model? What if the target model is updated while you are creating an attack?
Thank you. So in general, if we can access to the model, we can compute a gradient, then we can generate adverse example. But in some cases, we don't have the access to the model. Then it might be possible to use the transferability here. So we can train the different model, but that will give the same input-output pair. Then after having the new model, we try to generate adverse example on the new model, and that could work on the original model, which was not accessible to the attacker. Maybe again, Sakuma Sensei may be able to say something about this.
Okay, thank you so much. So usually this setting is called, this might be repeat of the Mori Sensei's question, but this setting is called black box setting. So by learning the substitute model by iterative access to the model, we can copy the model, and by generating the adversarial example to the substitute model, we can generate adversarial example to the model without having direct access to the model. And due to the transferability of the, it is well known that the adversarial example universally works with different models. So the adversarial example can fairly work in the black box setting. So I hope this can be an answer. So due to time limitation, the next one is the last one. So does an attacker need to know the inner model in order to know the types of adversarial attacks that would work against it? Or is there common types of attack that works in specific types of machine learning model? Example, attack ABC usually works against ECG models. Little bit hard to interpret the question. Mori Sensei, do you have any answer?
Actually, I was thinking about something, but yeah, actually, that was not that clear to me, sorry. We want to estimate the type of the adverse attack, like, I don't know, the type means the way how we generate adverse example or something.
Yeah, it's not clear to me a little bit. Maybe the question is asking about the transferability of the adversarial example with different models.
Okay, then we have already discussed that topic.
Yeah, maybe the answer to the last question might be the answer to this question too. Okay, so if we have further question, maybe we can discuss again at the end of the seminar. So please ask again. Thank you so much. So, okay, thank you so much, Mori Sensei. So please thank to the speaker. So can we switch the speaker? Next speaker is Akimoto Sensei.
Okay, hello everyone. My name is Yohei Akimoto. I'm from University of Tsukuba. Today I'm going to talk about minimax optimization problem. Minimax optimization with approximate minimization solvers and its application to automatic person control. So this work is a joint work with researchers from Osaka University. First, let me introduce our motivational application, which is automatic person control task. An automatic person control task is a task to control a subject ship toward the target position near a berth while avoiding a collision to the berth. To obtain such a controller, first, we designed a state equation model of a subject ship where S represents the state vector, A is the action vector, and Y is the uncertain parameter, which, for example, consists of coefficients in the state equation model, weather conditions, and so on. Although Y in the real environment, denoted by Y real here, is unknown, we need to estimate it to perform a simulation. Let Y sim be the estimated value. Then finally, we try to find a controller parameterized by X that minimizes the cost function f x y sim computed through simulation using Y sim. The obtained controller is supposed to work well on a simulation using Y sim, However, due to the difference between the simulation and the real environment, it doesn't necessarily work as well on the real environment. And it may cause a collision to the burst like this, which must be avoided for safety. Okay, now we talk more about general illustration. As we saw in the motivational application, we often rely on the simulation-based optimization to obtain a solution that is supposed to work well on the real environment. However, it is often difficult to build an accurate simulator, or it is even impossible due to some uncertainty in the real environment. Then the difference between the simulation and the real environment makes the solution obtained in the simulation unreliable in the real environment. A good solution for simulation is not necessarily good for real environment, which is problematic, especially when a low quality solution tends to have a safety issue. Since we want to obtain a solution that performs well on the real environment rather than on the simulation, we need to deal with such an uncertainty during the optimization. One way to find a solution robust under the uncertainty is to formulate the problem as a minimax optimization problem. In a minimax optimization problem, instead of estimating y real by y sim, we estimate a set, here denoted by capital Y, of uncertain parameter values, including y real, which is more realistic than assuming the accurate estimator. Then we minimize the objective function value under the worst scenario in capital Y. In this way, we can guarantee that the performance in the real environment is upper bounded by the worst case objective value, as long as the real environment is included in the capital Y, the predefined uncertain set. In this work, we are going to tackle these minimax optimization problems where we assume that the objective function value is computed through simulation, and hence it is black box. Therefore, we assume that the worst case objective function is not analytically available, and possibly the objective function is not convex concave, and its gradient is not available. Compared to the cases where the gradient is available, the minimax optimization in the derivative-free situation has not been well investigated. Therefore, in this work, our objective of this work is to design our derivative-free approach for minimax optimization problems. Also, our ultimate goal is to locate the global optimizer of the worst case objective function. It is often impractical to try to locate the global optimal solution unless we can assume a very nice property of the problem, such as convex convexity. Therefore, we will set a more realistic goal here. In case of non-convex minimization problems like this, a solver is often designed to locate a local minimum rather than the global minimum as fast as possible, Yeah. Then we perform this start until we get a local minimum point with a satisfactory objective function values. So in our minimax optimization setting, a locally optimal solution may be defined by a local minimax saddle point, which is a local minimum in X and local maximum in Y. Therefore, we set our goal as to locate a local minimax saddle point as fast as possible. And in practice, we perform these starts until we obtain satisfactory solutions. Okay, now we focus on how to obtain a local minimax saddle point. A popular approach when the gradient of the objective function is available is a simultaneous gradient descent ascent approach summarized here. It simultaneously minimizes the objective function value with respect to X and maximizes it with respect to Y. Here, eta is the line grade. This type of approach has been recently popularized by the success of generative adversarial networks, and its convergence properties have been theoretically investigated. For example, on strongly convex concave functions, where f is strongly convex in X and concave in Y, It has been shown that the simultaneous gradient descent ascent update converges linearly toward the global optimal solution if the learning rate is sufficiently small. So, inspired by the simultaneous gradient descent ascent method, we propose the simultaneous descent ascent method relying only on a derivative-free approximate solvers. Here we suppose that we have a derivative-free numerical solvers for this minimization problem and maximization problem. They are denoted by mx and my. Given the current estimate of the solution, xt and yt, the first approximate solver, mx, return a solution that is better than the current xt under the current yt, unless xt is already a local minimum. And similarly, we suppose that my returns a solution that is better than current yt under the current xt, unless yt is already a local maximum solution. Assuming that we have such approximate solvers, we update the current estimate of the minimax saddle point by moving toward the output of the approximate solvers by using the line rate iter. So compared to the gradient-based approach shown in the previous slide, we replace the negative gradient and the gradient with the difference between the current estimate and the output of the approximate solvers. This way, we can construct the derivative-free saddle point optimizer. Now, research question here is whether we can guarantee the convergence of this algorithmic framework as we can guarantee for the gradient-based approaches and how fast it converges. One thing that we can easily see from this update formula is that the stationary points of this update formula are all local minimax saddle points. So as long as it converges, its limit point is what we want to obtain. To further investigate whether this approach converges, we analyzed our approach on strongly convex concave problems. Since a smooth objective function can be approximated by a convex concave function around locally minimax saddle point, we expect that the analysis on a convex concave function will provide us an important insight. To guarantee the convergence, we further assume that the approximate solvers output a solution with a function value epsilon times smaller than, epsilon times closer to the optimal value than the current value, which is summarized here. If the approximate solvers satisfy these conditions, then in addition, if the learning rate iter is sufficiently small, our approach is guaranteed to converge linearly toward the global minimax saddle point, which is the same type of convergence speed as what we can guarantee for the gradient-based approach. From this theoretical investigation, we show the goodness of the proposed approach. However, at the same time, this result indicates that we may need to set the learning rate sufficiently small, and the upper bound of the learning rate to guarantee the convergence may depend on the problem characteristics. For example, let's consider the convex concave quadratic function defined here. The upper bound of the learning rate iter is then explicitly written as inequality at the bottom here. The important message is the first term, 1/1 plus sigma squared, where sigma is the coefficient determining the effect of the interaction term between x and y in the objective function here. The message is the more interaction x and y have in the objective function, the smaller the learning rate needs to be. Since we are considering a black box optimization setting, such an problem characteristic is not available to the algorithm. This will make the algorithm difficult to use in practice as it is difficult to choose a light iter. Therefore, we have developed a heuristic approach to adapt the learning rate. In a standard minimization problem setting, we may be able to use a speed of decrease of the objective function value as an indicator for the adaptation of the line glade, because the objective of the line glade adaptation is to maximize the speed of convergence. However, in minimax optimization problem, we cannot rely on the objective function value itself, as it is not amount to be decreased or increased monotonically. Instead, we define a so-called suboptimality error, which is denoted by G. It is a difference between the worst case objective function value under the current X and the best case objective value under the current Y. If a point has 0 error, it implies that this point is a global minimax saddle point, which means global optimal solution for the minimax problem. Moreover, if F is convex concave, the opposite is true. Therefore, we basically want to decrease the error as fast as possible. From these observations, we employ this error function as the indicator for the line glade adaptation. The idea of our line glade adaptation is as follows. We sample a candidate line glade along the current estimate of the best line glade, then run the algorithm for a while with the selected line glade, estimate the speed of decrease of the suboptimality error. Then if the estimated convergence speed is better than the previously tested line glade, then we update the estimate of the best line glade, and otherwise we don't. Now to see how well the proposed line glade adaptation mechanism works, we tested our approach on a convex concave quadratic problem shown here. We implemented the approximate solvers with the so-called 1+1 scenarios. It is a well-known approach for black box continuous optimization. For each solver call inside our approach, it spent the objective function calls of around 25 times the number of variables to be optimized, and it returns the best solutions. The results are summarized in the figure on the right. The vertical axis is the number of F calls until the suboptimality error of less than 10 to the power -5 is achieved. We tested the proposed approach with adaptive line glade, which is denoted by adapt, and one with the fixed line glade, where the line glade is the theoretically derived optimal value, which is denoted by eta star, times the number of numbers displayed here. We first remarked that the fixed line glade strategy failed to optimize this problem when the line glade is equal to or greater than the theoretically obtained upper bound, which is 2 times eta star, which should be here, but it's missing because it failed to optimize. And the best convergence speed was achieved along the line glade close to the theoretically optimal value here. And the smaller the line glade is, the longer the runtime becomes. The adaptation mechanism managed to optimize this problem like this by compromising 2 to 3 times more functional evaluations, F calls, than the best fixed line glade situation. Now we apply our approach to version control task presented at the beginning of this talk. Again, the objective is to obtain a controller that moves the subject ship from the starting point toward the target point, which is located near the bars while avoiding the collision to the bars. The control subject ship is a 3-meter model ship. The state equation model is modeled by MMG model, which is a standard maneuvering model. The controller is modeled by a neural network with 99 trainable parameters. The uncertainty parameter consists of 10 coefficients of the state equation model regarding the wind force. In previous studies, these coefficients are estimated by using the basic information of the subject ship, like length and width of the ship. However, it has been reported that fine-tuning is required to model this ship maneuvering accurately. We designed the uncertainty set capital Y to be the interval on the estimated value, like this. The objective function is designed to measure the distance between the final position and the target position, plus the penalty about the collision to the bars, to avoid collision to the bars. We use the 1+1 CMAES as the approximate slopes for both MX and MY. We compared our approach with two baselines. The first baseline is that minimizes the objective function under the estimated uncertain parameter like this. And the second baseline is, well, it samples 100 points uniform randomly in the predefined uncertainty set, capital Y, and it minimized the worst case objective under the sampled 100 scenarios. For all approaches we performed, we start until 1 million function calls has been spent, which amount to approximately 24 hours for each trial. These figures show the result of 8 independent trials for each approach. The top figure shows the objective function value under the estimated uncertain parameter. And the bottom figure shows the worst case objective function value inside capital Y. Obviously, the first baseline performed the best in the simulation using the estimated uncertain parameter values, because this baseline is optimizing this function. However, the worst case performance was deteriorated, and the obtained controller failed to avoid collision in 4 out of 8 trials. The loss function over 10 implies that this controller failed to avoid the collision to the bars. And the second baseline achieved better worst case performance if we consider the median performance, which is denoted by orange bar. Yet 3 out of 8 trials failed to avoid collisions. On the other hand, proposed approach succeeded to obtain a controller without collision in the worst case, like this. Here we compare the obtained trajectories. The left one is the trajectory observed for the controller obtained by the first baseline, which minimized the objective under the estimated coefficient. The ship, in this case, ship moves straight toward the target position. So it looks quite nice. However, it somewhat overshoot and collided to the bars, which is, well, not visible in this picture, but it collided. So the light figure is the trajectory obtained for the controller obtained by the proposed approach. It obtained a rather different control rule. So the ship first becomes perpendicular to the bars, then move back toward the target position. It may be understood as minimizing the wind force toward the bars by making the ship perpendicular to the bars. Then the influence of the uncertain coefficient regarding the wind force will be minimized. This may be helpful to achieve a good worst case performance. Okay, we summarize our talk. We analyze simultaneous descent ascent with approximate slopes on convex concave problems, strongly convex concave problems. Linear convergence has been proved for a sufficiently small line rate. As far as I know, the linear convergence result in a derivative-free setting is a unique result of this work compared to related work. which we skipped for time limitation. We propose a heuristic adaptation strategy for the line rate. Such an adaptation strategy is important to make the algorithm practical in black box optimization setting, and a numerical study showed its promising performance. Finally, we applied our approach to robust person control task with uncertainty in the state equation model regarding the wind force. Controller without collision to the burst have been obtained in all trials. This is the end of my presentation. Thank you very much for your attention. And if you have any question, you can write a question to the Q&A box. Thank you.
Okay, thank you for the talk. So up until now, we have no question from audiences. So if we have any question, please submit your question to the Q&A box. So let me ask one question from me.
Yep.
Maybe I missed the detail, but let me ask again. So you have some guarantee on the linear convergence of the strategy, right?
Yes.
So, and I guess the guarantee is given that the function is convex and concave for x and y, right? So, yes. But in your application problem, as long as the neural network is used, the function is not convex and concave, right?
Yes.
So is there any guarantee or any suggestion on the performance when the function is not convex and concave?
Thank you for asking this question. And yes, so in a practical application, we cannot guarantee the convex concavity. So we cannot guarantee the convergence. And so far, we don't have any theoretical guarantee for the convergence itself. But the first thing that we can say is, so if it converges, it is guaranteed to be a locally minimax saddle point because of this construction of the algorithm, which is one thing that would be helpful, because if you observe the convergence, then it is local minimax saddle point. And but it doesn't guarantee the convergence. And the comment about what would be the implication of this to the application is that, so basically, if there is a local minimax saddle point in the application, then in the neighborhood of this local minimax saddle point, the function can be approximated by the convex concave function in the neighborhood. Then it doesn't necessarily imply, but we conjecture that this convergence speed, so here I didn't show the convergence speed, but I derived the convergence speed and the upper bound for the learning rate in the general case. And this may be helpful to understand the convergence speed itself to a local optimal solution. So, yeah.
Okay, thank you so much. So maybe we have no question up until now, so we can switch the speaker. Let's thank to the speaker. Thank you so much.
Good afternoon. My name is Hiroshi Uno from University of Tsukuba. Let me start my talk. I'm going to talk about applications of machine learning in formal methods. And I'm a formal method researcher. So first of all, what are formal methods? Formal methods are mathematically rigorous techniques for developing reliable software and hardware systems. And main research topics of formal methods are formal specification, verification, and synthesis for developing provably correct programs. Complementary method to formal verification is well-known testing, which is for finding bugs in the target. We also study fault localization, localized bugs, and automatic repair of such bugs. Another interesting topic is language-based security and privacy enforcement. Formal methods applied to prove security and privacy properties of the target systems. And traditional approaches in a formal method have been based on automated deductive reasoning, such as theorem proving, constraint solving, and so on, which is in stark contrast to machine learning, where inductive reasoning instead of deductive reasoning is automated. Let me explain formal verification and synthesis in more details. Program verification is a task of formally proving or disproving a mathematical proposition. Intuitively means that the given program satisfies its formal specification. This formal verification gathers great attention from industry and academia. For example, Microsoft applies formal verification to device driver verification, and Facebook recently applies formal methods to mobile applications, verification of mobile applications. Also, Turing hours have been given to theoretical and practical developments in formal methods. And let me explain program synthesis. On the other hand, program synthesis takes a partial program with holes to be filled and its specification phi, and outputs an executable program P that satisfy the specification. The specification can express what the target program P computes and how P computes the results. It means, for example, resource limitation, such as time, space, and energy. Okay. And phi can be represented in various forms, such as logical formula, input-output examples, and natural language sentences. So enabling technologies of program verification and synthesis are following: program logics and constraint solvers. Program logics are for mechanizing verification and synthesis. The most famous program logic is Hoare logic for proving Hoare triples, PCQ, which means that for any initial program state sigma that satisfies the precondition, if the execution of the program C under sigma terminates, the postcondition Q is satisfied the resulting state. To automate verification and synthesis, constraint solvers are used. The famous solvers are SAT and SMT solvers. SAT solvers are for checking the satisfiability of propositional formulas. And SMT solvers for predicate formulas over first-order theories over various data structures, such as integers, reals, lists, arrays. In program verification and synthesis, we also use CSC and SIGA solvers for for solving constraints, second-order constraints over functions. Functions are unknowns here. Functions represent loop invariants of the program that witness the program satisfy the specification, and programs to be synthesized. So formal methods, the main targets of formal methods have shifted depending on the requirements from the industry. Hardware to low-level software, high-level software, and recently main targets are machine learning and cyber physical systems. They're very challenging targets because they tend to be large, black box, non-modular, and uncertain. Traditional approaches that use deductive reasoning alone are hard to scale to those systems. And existing techniques fall short in quantitatively modeling and reasoning about uncertain behaviors. To address the first challenge, we integrate with data-driven inductive reasoning based on machine learning for scalability. To address the second one, we extend formal models, logics, and systems with non-determinism and probability for handling uncertainty. So this is an excerpt from the list of accepted papers of the coming computer-aided verification conference, which is the top conference of formal methods. Judging from the title of the papers, at least 18, including our two papers, are related to integration of formal method and machine learning. Popular topics are verification of neural networks and safe reinforcement learning. That is applications of formal method to machine learning. Another direction we are working on, our papers are on applying machine learning techniques to formal methods. So in this talk, I will focus on program verification and synthesis based on constraint solving and machine learning over functions. I will first use examples to explain how to reduce program verification and synthesis problems to constraint solving. Then I show you how to solve constraints via integrated deductive and inductive reasoning. Deductive reasoning is performed by theorem proving, such as SAT, SMT solvers. And inductive reasoning is performed by machine learning. Okay, let me explain, move on to the first part. Program verification is reduced to constraint solving. Given a target program P and specification psi, we generate a set of constraints C on function variables. We then solve C, and if C is satisfiable, then the program satisfies the specification. If C is unsat, then P violates the specification. Here, the class of constraints representing the target constraints can be regarded as a verification intermediary independent of particular target and method. One of the most famous classes of such purpose is constraint home clauses, CSCs, constraints over predicate variables. Many tools for generating constraints for Java, C, and OCaml have been developed. And highly efficient solvers for solving CSCs have been also developed and publicly available. Well, this is a formal definition of CSCs, but actually you don't need to understand this slide to understand the rest of my talk. This is for those who love formal definition, so I will skip it. Let me use an example to show how constraints are generated and solved. This is an example for a triple consisting of precondition, program, and postcondition. This whole triple states that if the initials, so this program has two variables, x and y, and x0 represent the initial value of the variable x. Okay, and the precondition says that if the initial state satisfies the precondition x equals x0, and the while loop terminates, then the postcondition is satisfied by the resulting state. Please note that this statement is satisfied, this holds. I will explain why later. So given the input program and specification, these three clauses, constraints are generated. Here, I represent the loop invariant. I is a predicate variable representing loop invariant of the program. Loop invariant intuitively means loop invariant is a condition that always holds at the beginning of the loop, at the head of the loop. It is the predicate variables is among three variables, x0, which is actually constant, doesn't change, and x and y. And the first clause requires that after the assignment of 0 to the variable y, the loop invariant holds. The second constraint says that the loop invariant is preserved by executing the body of the loop once. And the third clause requires that the loop invariant and the negation of the loop condition implies the post condition. This means that when the loop terminates, the post condition must hold. Okay, and this constraint is satisfiable. And actually, this is a solution of the constraint set. By substituting this solution to the predicate variable, all the clauses, constraints are satisfied, become valid. The solution says that the sum of the value of the variables x and y are always equivalent to the initial value of x. This is why the specification holds. Okay, and the goal of constraint solving to find such a solution of C. Okay. Let me next explain program synthesis via constraint solving. Similarly to the case of program verification, given a programming language L and a specification psi, we generate a constraint set C on function variables, and C is satisfiable. Then some program in the language satisfies psi. If C is answered, then all P in the language violates psi. We generate constraint set to ensure these conditions. And similarly to the case in constraint program verification, the constraint set can be, the class of constraints is regarded as a synthesis intermediary independent of particular target and method. And the most famous class of constraints is SIGAS, syntax guided synthesis, SIGAS. And efficient solvers have been developed for the class of constraints. Okay, this is a bit formal definition. And I can skip this safely, and I will use an example SIGAS constraint to explain. Let us consider the language where the set of all terms of linear integer arithmetic function. And let us consider this specifications phi. And f is a function variable with two arguments, two integer arguments x and y. This is the synthesis target. The specification requires that for any integer x and y, f of x and y should be greater than or equals to x and y, and the return value of f is either x or y. Okay, and from this specification and language, we obtain this set of constraints, which is almost equivalent to the specification and need no explanation. And this one is satisfied by this function. Please note that this function represents the maximum function of the two arguments. So the goal of constraint solving to find such a function for the given constraint set. Okay. Let me move on to the second part, where I will explain how to solve constraints via integrated deductive and inductive reasoning. Well, and there are challenges in constraint solving. The problem is undecidable in general, even for decidable theories. So we need to rely on heuristic approach to solve such constraints. However, the search space of solutions is often very large, high dimensional, and non-smooth. To address these challenges, researchers are integrating deductive and inductive reasoning techniques within the framework of counter-example guided inductive synthesis, CGIS, with an expectation that a general solution form can be inductively learned using a machine learning technique. And then details are completed by inductive methods, such as theorem proving. Okay. Let me explain CGIS, counter-example guided inductive synthesis learning framework. It iteratively accumulates example instances E of the given constraint set C through the two phases for each iteration. We repeatedly iterated these two phases. In the synthesis phase, a learner finds a candidate solution role that satisfies all the examples E corrected so far. And in the validation phase, teacher checks if the candidate role also satisfies C using an SMT solver deductive approach. And if yes, we can return role as a genuine solution of C, the original constraints. Otherwise, we repeat the procedure with new example instances that witness non-satisfaction of C by role added. Oh, okay, let me show you an example run of CGIS using this constraint set consisting of 3 clauses and 1 predicate variable, which is, this is simpler one than I showed you before. The learner, starting from the empty set of example instances, the learner first find a candidate solution that satisfies E. So any solution is, any candidate is okay. Here, for example, let us consider this one. And this means tautology. Then the teacher checks whether the candidate is genuine or not. And in this case, teacher says no, because the third clause is violated when x equals 0, because x equals 0 doesn't imply contradiction. This means contradiction. Okay. Then we instantiate the third clause with the value and obtain this example instance. which is simplified to this one. This means that I doesn't satisfy 0. I must not satisfy 0. This means negative example of I. And from this, the learner finds a second candidate like this, for example, like this, x is less than 0, which satisfies the negative example, and asks the teacher whether it is genuine or not. And the teacher again says, no, this is not a genuine solution because the first clause is violated when x equals 1. Okay. Then we obtain this example by instantiating the first clause, which represents this positive example. I should contain 1. This is a positive example. And from the example instances is the learner finds a new candidate. This time, for example, we obtain this one, which is, however, not a genuine one because the second clause is not satisfied. When x equals 1, by instantiating x with this value, concrete value, we will obtain this constraint. I of 1 implies I of 0 or I of 2. Please note here that this example is not neither positive nor negative. We have to handle such a kind of constraints. Finally, the learner finds this candidate, which is genuine. This satisfies the original constraints. So we are done. Okay. This is SIGIS learning procedure. Let me compare SIGIS with online supervised learning. Similarities are as follows. Learner trains a model to fit examples E and obtain candidate role. And also teacher requires role to generalize to C. It means that role shouldn't overfit E examples. But we have many differences. E is usually assumed to have no noise and it sees hard constraints instead of soft constraints. So role is required to exactly satisfy all the examples in E, or there's no chance to satisfy the original constraint set C. Also, role should be efficiently handled by the teacher. And sampling of E from C is not from identical independent distributed. So it depends on role and teacher. Also, E may contain not only positive and negative examples, but also arbitrary clauses 1. So I think this setting is kind of similar to weakly supervised learning. Okay, despite these differences, machine learning techniques turned out to be quite useful and have been applied to SIGIS. There are many work that adapt ML models and algorithms to implement learner. We use linear classifiers, decision trees, support vector machines, neural networks, graphical models, and reinforcement learning, and so on. And we have developed a constraint solving tool called PCSAT based on the references in blue, which is available from here, and which worked pretty well. Let me explain future and ongoing research before concluding my talk. So PCSAT works very well, but we thought we want to extend it to enable more scalable synthesis of more expressive functions from more expressive constraints. I mean, for scalability, we are working on applying advanced ML techniques such as language models, and weakly supervised learning to improve SIGIS. We are also supporting functions over advanced data structures, such as linked, tree, array data structures. We want to synthesize these complex functions that manipulate these data structures. We are also supporting nonlinear and probabilistic constraints, which are necessary to apply our technique to verification of models with uncertainty, which is usual in ML community. We are also working on applications of formal methods to machine learning. This is the other side of the coin. For example, we are working on probabilistic termination analysis and security and privacy verification of probabilistic programs. And we are also planning to apply our technique to robustness verification of machine learning models. But as you already see, verification of neural networks is very popular in the formal verification community. And I don't want to work on such a red ocean topic. So I'm considering other important ML models. Okay, let me summarize my talk. So I have explained how to reduce verification and synthesis problem to constraint solving, and explain SIGIS-based constraint solving that integrate deductive and inductive reasoning to address challenges in formal method. Thank you for listening.
Okay, thank you for the talk. So if you have a question, please submit your question or comment to the Q&A box. So up until now, no question is submitted. So let me ask one question. This is a general question, but overall, the application of formal method to machine learning, in application of formal method to machine learning, I think the researchers in formal method follows the algorithm of machine learning, so that formal method works inside the framework of machine learning. But if you have some request to machine learning people, so that the formal method works well or fits well, maybe machine learning people may have may be able to, improve the machine learning model. So do you have some idea on that direction?
It's an interesting direction, although I don't have an idea. So you are proposing instead of directly using existing machine learning models and techniques, learning algorithm, machine learning people can suggest some modified models and algorithms that are more suitable to formal methods.
Yeah, maybe we can say like formal method friendly machine learning or something like that.
It's very interesting. Oh, I've never thought of that direction. Actually, I know some work in that direction, provable neural network, provably correct neural network or something like that, which extend learning algorithm for deep neural networks to guarantee the robustness of the learned model. Actually, I found that work in your slide at IB's ML conference or something like that, which is one such direction. And I think that one is an interesting direction worth investigating. I'd like to work on such things.
Okay, I guess that is a certified robustness or something like that. So that is basically designed inside the framework for machine learning. So I guess it's not specifically designed considering the combination with formal method. But anyway, if that kind of algorithm has some good property to connect with formal method, that might be interesting for both of interesting to researchers in both fields. So maybe we can have discussion later.
Yes, thank you.
Okay, so if you have no question, we can finish this talk. Please thank to the speaker.
Thank you.
Thank you so much. If no question, we can close the session.